Okay, we're going to back up a little bit to build up some concepts we need for antiderivatives. We're going to back up to summation. Sigma notation is the notation that mathematicians used to represent they wanted to add up a lot of numbers. And this sigma, this weird looking E here, is the Greek letter S for summation, right? So we call it sigma notation, or you can call it summation notation. It's got this Greek letter. It's got what number you're supposed to start counting at. So that's the index of summation, I. You start counting at 1 and you go up to n. So that would be the upper bound. And this would be the lower bound starting at 1. It might start at 2 or whatever and go up to 10 or 15 or whatever. This is the ith term. It's usually some kind of little formula, and then you're going to plug in the numbers 1, 2, 3, all the way up to whatever that top number is. Just plug them in one at a time to whatever this formula is. That formula is called the ith term because it's a general form that represents any term, like the first term or the second term or the third term, and it's got the letter I in it, or whatever this index of summation is. It could be the letter J or K. I, J, and K are the commonly used ones. And then this is the expanded form here, all of this stuff here. And it's just, after you've plugged a number 1 into whatever this formula is, that answer goes here, and that's the first term. And then you plug the 2 into here, whatever that formula is, and that answer would go here. And then the summation, the sigma here, represents that we're supposed to add up all those answers all the way up to the term that you get when you plug in that last number, that top number there. And then the answer would be the sum of all those numbers. I know you've seen this before. We're just reviewing it because we need to understand it to get the understanding for the next part of calculus. So if we do the summation of I, first let's expand it. So here's the ith term. That's the little formula that we're going to plug 1 into. Not much to do here. You just plug in the number 1, and then you plug in the number 2, and 3, 4, 5, and we know we stop at plugging in 6 because that's the top number. And then you would add those together. So 7, 14, 21. Or we can start at 3. Notice our index of summation is j this time, and our ith term, or jth term in this case, is j squared. So we're going to put a 3 in there and we'll have 3 squared. Then put a 4 in and get 4 squared. And then 5 squared and 6 squared, and I know the last number I plug in is 7 squared because that's my upper bound. So I'll have 9 plus 16 plus 25 plus 36 plus 49. And we can all do the math on that. 135. All right, so that's just some real basic reminders of what that is. Here are a lot of summation formulas that will help us do it a little quicker, because we won't always have numbers like 3 to 7 or 1 to 6. This is, I believe it's labeled Theorem 4.2 in your book, so in the homework when it says refer to Theorem 4.2, use these formulas. That's what they're talking about. So if we want to sum up a constant, like we want to do the summation of the number 4 from 1 to 3, well, there's no place to plug in that number, so that's just my first term, because we're not really plugging in a number. There's no I there. So my second term is also 4. My third term is 4. So first, second, third, I know I stop at 3 because I have 3 up here. And so then that would just be 12. Well, you can see that a shortcut might be just take that constant times the number of terms that you're adding up. So that's the summation of a constant. That's the formula for it. It's just a shortcut so that you don't have to write it all out, expand it out, and do all the math. So it's whatever that constant is times however many numbers you're doing. So that n would be on top here. All right, if we want to do the summation of the number of I, that's going back to what we did here. You can just add them all up. That's the long way. But what if you wanted to do 1 to 100? There's a fun story about Gauss I can tell you about. So if we're going from 1 to n, here's the shortcut. You take the top number times 1 higher than the top number, and sorry, that's divided by 2. Not n. All right, then the third formula, if you want to add up all the I squareds, Here's the shortcut. That top number times 1 higher than the top number times 2 higher than the top number, and then divide that by 6. I'm just going to verify that. It looks a little off to me, but so theorem 4.2. Yeah, I knew that was wrong. Whoever made up this slide? Oh, that was me. All right. So it's n times n plus 1 times the quantity 2n plus 1. And yeah, I have this one right. The summation from 1 to n of I cubed is n squared times n plus 1 squared over 4. So you can see that these formulas make it a lot easier than doing it the long way, especially if we had to sum up the numbers from 1 to 100 or 1,000. These little formulas are just based on that top number. So anytime you have any part of your summation that has an I squared or an I cubed or an I, you can use the formula for part of it and a constant. So we're going to try to break up our summation formulas using constants and squareds and cubes and i's and create formulas so that we don't have to expand every problem. But on the easy ones like this, just expand them. They're pretty easy to do if it's a small number. All right, so let's try this one. If we want to evaluate the summation from 1 to n of 1 plus I for numbers 10 and 100 and 1,000. Well, for 10 it would be pretty easy. Just plug in 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, all the way up to 10 plus 1 and add those answers together. But let's use our new summation formulas to break this down a little bit. So the summation of I and then the summation of 1. So it's almost like we're distributing the summation in. We can do the summation of separate parts of a sum and then add the answers together, and that will still be the same as if we had done it in the reverse order. So now that we've separated this, this matches one of our summation formulas. It's the summation formula n times n plus 1 over 2. And since this is a constant, I don't know why there's a dot there, that's just the number 1. That constant, we can use the constant formula, which is 1 times n. So now we've rewritten the summation in terms of n, so now we can just plug in these numbers and calculate each one separately pretty quickly. So 10 times 11 over 2 is 55, plus 10 is 65. Or we can do it for 100. 100 times 100 plus 1 is 101, divided by 2, times 1 plus 1 times 100. And that's 5150. So you can see how that works. We can do that for any summation. We're just going to break it up over the pluses or minuses and then do a formula for each piece of it. And if we had the summation of like 3i squared, you can pull that constant out and just do the summation of I squared and then do 3 times the answer. All right? So the graphing calculator also helps us with summations. If you go on your graphing calculator and you push the second stat, excuse me, then let me bring up the graphing calculator here if I have time. You're going to push second stat and then go over to math, and then go down to number 5, and that brings up the word sum. And we're going to do a sum. And then push second stat again and go to ops and go down to number 5, and that gives you sequence. So you're going to have sum sequence. It's the word sum first and then the word sequence after that. So it's going to look like this. You're going to have sum on your home screen and then sequence. So on the graphing calculator, better clear this out here. All right, we're going to go to second stat, go over to math, and go down to number 5 to get the word sum. Then keep that on your home screen and go to second stat again, go over to ops, and go down to sequence. Hit enter. Oh, did I do the wrong thing? I did cumulative sum instead. Oh, I did 6. There we go. Okay, you get some sequence. Then you put in your formula. Now, you could use I, but you might as well use X. So let's do the summation of I plus 1 like we had in the previous example. So we'll do X plus 1. And then you're going to use, so that's where the function goes here. And then we're going to type in the X, and then our lower bound and our upper bound, and then what we want to count by. So we want to type in a comma and then X. Here's the comma, and then X, and then comma. And our lower bound is 1, and let's just go up to 10. And then count by ones. Then close the parentheses, and close them again, because you had 2 parentheses open. And then hit enter. And 65, that was the answer we got. So if they get really cumbersome, go ahead and use your graphing calculator, and there is part on your homework that says use the graphing calculator. So there's the order of things to do and what the syntax should look like when you're done. There's your homework, page 267, 1 through 23 odd.